discussions on the minor structures that develop in a rock as a result of applied directed stress. In the next 3 episodes, we will be discussing foliations or secondary planar structures that develop in a rock, lineations, that linear structures that develop in a rock as a result of applied directed stress, and in this episode we will be discussing the geometrical and genetic relationships between the foliations, lineations and major folds. If you remember the mechanism of fold formation, especially the buckle or flexure slip folding, where the directed stress responsible for the fold formation is applied parallel to the layering, the axial plane of the fold is naturally developing perpendicular to the applied directed stress. Apart from this, in case of passive shear folding, foliations, especially the disjunctive foliations, they develop parallel to the planes of shear, the shear fractures that are responsible for the formation of folds. In case of passive shear folding, the foliations develop parallel to the axial planes of the passive shear folds. There is another mechanism of foliation formation or cleavage formation, which is known as pressure solution. The resulting foliation usually called solution cleavage. What happens is that when a pre-existing planar structure in a rock is subjected to layer parallel directed compressive stress, the materials which can be easily dissolved like quartz, they are removed from the limb regions of the folds because these are regions of high stress and get deposited in the hinge zones of the small folds, which are regions of low stress. Thus, after some amount of time has elapsed, the deformation has progressed a little. On the pre-existing rock, a secondary foliation is imposed in which there is a distinct banding. The insoluble minerals like mica, they remain on the limbs of the folds, while the soluble minerals like quartz, calcite, etc., they are dissolved and deposited at the hinge zones of folds, which are low stress zone. Thus, across the pre-existing planar structure, a secondary foliation, alternate banding of mica rich minerals along the limbs and quartz rich bands along the hinges develop, resulting in the development of a axial plane parallel secondary foliation. This is known as solution cleavage. Now that we have studied the different types of secondary foliation, we can see that foliations are products of mostly are products of applied directed stress, either layer parallel or at a high angle to the layer. As a response to this applied directed stress, the minerals existing in the rock either gets reoriented or change their shape to the most stable position against the applied directed stress, and thus a preferred orientation, a parallel alignment of these mineral grains form in the rock, resulting in the development of secondary foliation. Thus, secondary foliations are very useful in understanding the direction from which the major directed stress was applied. We will be discussing about it in our next episode while we discuss the relationship between foliations and the major folds. Let us discuss the relationship between secondary foliations and regional structures or folds formed during the same deformation. As we have discussed during the mechanism of folding episode and while describing the different types of foliations, foliations are almost always developed perpendicular to the direction of maximum stress or directed compressive stress in case of buckle folds, so that the axial plane develops perpendicular to the direction of maximum compression, and the foliation also develop either parallel or systematically disposed against the axial plane of the regional structure, showing a convergent fanning. The relationship between the axial plane and the fold is this, that the acute angle seen on the profile section between the cleavage, axial planar cleavage and the bedding opens up in the direction of fold closure. Thus, even if the closure of the major fold hinge is not observed in the field, we can find out the sense of closure by noting the direction in which the acute angle between the axial plane cleavage and the bedding is closing. If we view it on plan, we can know the direction of closure, and if we know the direction of plunge of the hinge line, that is the line of intersection between the axial plane cleavage and the layering, we can easily identify the fold as an antiform or a synform. Thus, the rule formed by George Pumpelly, that says that the acute angle between axial planar cleavage and bedding opens up in the direction of closure, helps us in identifying the closure of the major fold by studying the relationship between the axial planar cleavage and bedding. The line of intersection between these two always gives us the orientation of the regional hinge line. So, by combining these two, we can easily identify the major fold closure. By identifying the major fold closure, we can analyze and interpret the direction from which the stress came, what the broad tectonic scenario was. In case of passive shear folding, however, there is no convergent fanning or variation in orientation of the cleavage on both sides of the axial plane. The cleavage plane develops perfectly parallel to the axial plane, along which the layering has been displaced to form fold. Thus, in case of passive shear folds, the axial planar cleavage is always strictly parallel to the axial planes. The foliations that develop in other types of folds, like the discrete and zonal crenulation cleavage, they are always parallel to the axial plane. There are hardly any situation where a secondary foliation developed during the same deformational phase as the major regional fold develops at an angle to the axial plane, except for the convergent fanning in case of buckle folds or flexure slip. While discussing buckle folds or flexure slip folds, we must keep in mind that the orientation of the cleavage planes systematically disposed against the axial plane is different in the competent and incompetent layers. If we go back slightly to the mechanism of folding, in competent layers there is extension along the outer arc and compression or shortening along the inner arc, while in the incompetent layer, where the deformation is passive, the upper competent layer and the lower competent layer, they direct the state of strain within an incompetent layer. So, within an incompetent layer, the radial cleavage planes disposed systematically against the axial plane show opposite sense of convergence. Axial planes in incompetent layers show convergence away from the core of the fold, which is known as divergent fanning. So, if on a profile section of a multi-layered fold we see alternating layers showing convergent and divergent fanning, we can directly know that the fold have been produced by layer parallel compression or flexure slip. This variation in orientation of the axial plane in axial plane cleavage in competent and incompetent layers, convergent fanning in the competent layers and divergent fanning in the incompetent layers, result in what is popularly known as the cleavage refraction. The cleavage planes appear to be refracting from one layer to the other. Otherwise, there is no significant deviation of secondary foliation from the parallel to the axial plane or symmetrically disposed around the axial plane position. Now that we have finished discussing about the definition of a foliation, the different types of foliation, let us have a quick recapitulation. Foliations are penetrative structures found in rocks. They may be both primary or secondary in nature, but usually we consider secondary foliations developed as a result of applied directed stress as the main types of foliation. Foliations are subdivided depending on the spacing between the planes. When the spacing between neighboring planes are more than 10 micron, they are called spaced foliation, and if the spacing is less than 10 micron or there is practically no domainal structure defining the foliation, we call them continuous. We have seen how the spaced and continuous foliations are further subdivided into different categories. We have seen how the foliations develop. We have seen how the orientation of the foliations are broadly related to folding, which we will be taking up in greater detail in a later episode. In our next episode, we are going to discuss about lineations, more specifically secondary lineations, because when the platy minerals or flattened equigranular minerals are forced into a preferred orientation or parallel alignment, their long directions oriented parallel to one another imparts a linear structure to the rock. We discussed in our next episode, which will be secondary lineations. Thank you.